Galaxies and their CGM do not evolve in isolation. In fact, we should expect the CGM of massive galaxies, like those of the Milky Way, to be in constant interaction with infalling satellites. And we heard a bit earlier from Andy Fox and from Scott Lucchini about the potential for satellites to populate the halo with its cool gas reservoirs. But if those satellites are massive enough themselves, we should expect those satellites to possess their own CGM, which should be colliding with the gaseous halos of their central host. However, despite the ubiquity of satellite CGM interactions in our universe and the role of satellites in shaping the global, thermal, and kinetic properties of the CGM, I know. However, despite the ubiquity of satellite CGM interactions in shaping the global thermal and kinetic properties of the CGM remains a poorly understood element of many models of the CGM. And this is a very crucial problem for us here at home, where we host our own pair of gas-rich satellites, the LMC and the SMC. And precision space-based measurements tracking the proper motions of the clouds over a multi-year baseline from the Hubble Space Telescope and later from Gaia have better constrained their kinematics. And we now believe that the LMC and the SMC are on their first passage of the Milky Way and moving at very large velocities with respect to the galaxy, on the order of over 320 kilometers per second. In addition, dynamical estimates of the LMC in particular put it at 10%, maybe even 20% of the total mass of the Milky Way. So putting these two things together, this means that the infall of the LMC represents a large and a recent perturbation to our galaxy. And if the LMC indeed hosted its own CGM, then its first infall offers us a prime opportunity to study the interaction between the LMC and the Milky Way, but their respective CGMs in action. However, most of this work about the interaction between the Milky Way and the LMC is largely centered on its collisionless components, its dark matter and its stellar halo. And so here's this very nice graphic from Nico Gavrito Camargo that as the LMC passes through the halo, it generates these density wakes in the dark matter distribution. This includes a transient wake that sort of traces the orbital trajectory of the LMC. You can think of this very similar to the Chandrasekhar dynamical friction wake. In addition to this sort of global dipole-like response called the collective wake. And this collective response is caused by the reflex motion of the Milky Way towards the LMC, which displaces the inner Milky Way towards the LMC and away from the outer halo. And this reflex motion appears as this overdensity in the sky, where you have an overdensity of material in the northern hemisphere and an underdensity in the southern hemisphere. And this has led many predictions for the manifestations of this observational effect in the stellar halo, which is believed to be a tracer of this underlying dark matter distribution. So plotted here, these are radial velocities of stars in the Milky Way halo. This is from the H3 spectroscopic survey led by Charlie Conroy and from Vida Chandra. And when you smooth over these data, you see this all-sky dipole in the line of sight velocities, and this is believed to be this reported detection of this reflex motion across the entire sky. But what probably many of you are wondering, and what I also wondered 2 years ago, is what about the gas? How has the CGM of the Milky Way responded to this recent infall, and how is this interaction shaping the physical and kinetic properties of the CGM? And so to address these questions, I ran idealized simulations of a Milky Way-like CGM in ENSO with an infalling LMC with its own CGM, similar to the work from Scott Lucchini. So for our initial conditions, our CGMs began near approximate hydrostatic equilibrium with their respective dark matter halos, and these simulations are incredibly simple. So there's no interstellar medium, there's no radiative cooling, there's no star formation. You only have your CGM, your dark matter halos, and a stellar disk, just as a point of reference. So plotted here are the CGM gas densities in the ZY plane. And as we advance in time, you will see the LMC swoop beneath the disk as it falls into the halo, and the star here just marks the average position of the stellar disk. So that as the LMC begins its infall, it immediately begins to feel the ram pressure of the Milky Way CGM, which blows most of it into this sort of head-tail wind behind the LMC. And as both CGMs drive this collision, you see the emergence of this pressure wave that propagates through the medium alongside the LMC. And as we end here near the present day location, the current configuration, we can already see just by eye some noticeable features in the gas density, in the wake of the LMC, and in the pressure front. But if we want to be a bit more quantitative, we can look at the difference between some given Milky Way CGM quantity at the present day and compare that to a Milky Way in isolation. So plotted here is just the log of the density ratio of those two runs, one with an LMC infall and one without. And so from these sort of residual plots, the key features of the interactions become a bit clear. So first, you have the stripped gas of the LMC CGM that sort of tracks nicely along the pass orbit of the LMC, and you also see these very nice swirls from the Kelvin impulse instabilities along the interfaces. You also have the shock front from the CGM-CGM collision, and due to the large surface area of the collisions, you end up with a shock front larger than the virial radius of the Milky Way halo. And so you get these jumps in the density that extends over very large scales with respect to the halo. And the contrast is a bit off in this projection, but you can kind of also see the global collective response from the overall gravitational interaction. But this is just in the density. We can also look in other physical properties. We can look at also in pressure and in temperature, and you see that the interaction may have a very outsized effect on the global properties of the Milky Way CGM. In fact, these jumps that you're seeing in density, pressure, and temperature along the shock front are consistent with a Mach 2 shock, which is about what you would expect given the LMC's velocity. And also you see the stripped gas tail of the LMC CGM quite visible in the temperature, as well as the shock doing heating in front. So putting all these pieces together, we see that the infall of the LMC should be generating order unity enhancements to the physical properties of the Milky Way CGM from a combination of both gravitational and collisional hydrodynamic effects. And we can also look at the response in gas kinematics. So plotted here are the galactocentric radial velocities and tangential velocities for the CGM gas in the YZ plane. So in the radial direction, we also see evidence of this reflex motion signature, but in the gas, these are centered on the galaxy, and so the reflex motion on the order of 40 to 50 kilometers per second, which is about what we observe in the stellar halo, as well as this long extended tail from the stripped gas. It also has very large radial velocities on the order of minus 200 kilometers per second, consistent with some of the measurements we've seen for ionized material along the stream. While on the right, looking at tangential velocities, you also have very large tangential velocities, which are on the order of the current measured tangential velocities for the LMC. And of course, a great place to end on is what are some possible manifestations that this interaction could be having in current CGM observables. And I think a lot of this is still work in progress, and I'd love to talk with you all about these. But first, as a first order thing, you just look at the column density. So these are very simple, just as an observer in the galaxy, just taking measurements along every line of sight, estimate the column density. So this is for an isolated Milky Way, so no LMC here. Very featureless, exactly what you would expect. But then once you include the LMC, you get an enhancement of the column densities along the pass orbit. So that's that stripped ionized gas from the LMC CGM. And if you squint, you can also see some enhancement along the shock, which is slightly offset from the current stellar position of the stellar disk. We can also make predictions for the X-ray surface brightness. And so this is within a band of 0.2 to 7 keV, with assumed of a uniform metallicity of about 0.3 solar. And we suspect that the shock may also have some contribution to the X-ray emission observed across the sky, which would be very exciting for possible detections in current all-sky maps or for future X-ray observatories. And we also see some features from the corona itself, which may be present in current observations. And lastly, returning back to the reflex motion signature detected in the stellar halo, if this reflex motion is also present in the CGM, it should also be present in line-of-sight velocities of the gas. And so we can also make predictions for the all-sky line-of-sight velocities from the reflex motion, and you find a very similar dipole along the sky, in the northern and southern hemisphere, in addition to the contribution from the stripped gas and shock-heated material along the vicinity of the LMC. So with that, I'll leave you with some takeaways. But that's only a piece of the story. So if you want to learn more, then please check out the paper, which is now up on archive this week. And thank you. And of course, talk to me. Thank you.
Questions? Oh, wow. All right. Start with Andy.
Yeah, great stuff. Really, really nice talk. In terms of the observational predictions, have you thought about H-alpha emission? If there's this long bow shock between the two CGMs, could you pick up H-alpha or any other emission lines there?
Yes, H-alpha would be interesting. I think one thing that's kind of prevented us from going a bit more detail about some of those more warm gas detections is because since we don't have radiative cooling and that our CGMs are fairly simple, there should be a lot of multi-phase gas which should also be present along the shock front, which could also sort of lead to brightening of the H-alpha signal. So that's very interesting. But also there could be H-alpha emission just from the interface layers of some of this LMC CGM gas with the hot halo. And so I think there are a number of possible observables here. And of course, there are even more that we mentioned in the paper that I didn't get to, but that's a great one that we can talk about.
So,
hello.
Hi. So great results. So I'm curious, what is your predictions radius where you'd expect this reflex motion to show up? In other words, do you expect it to see in high velocity cloud population?
Good question. So no. And one reason why is because the reflex motion sort of gets stronger as a function of distance. And so if many of these HVCs are very close to the galaxy, the reflex motion contribution would be rather small because they're moving towards the LMC at very similar velocities as the disk itself. And so it needs to be a strong differential effect. And so the reflex motion doesn't really become that noticeable until you reach maybe 50 kpc away from the galaxy. Because in that case, you are seeing a very strong differential in the rate that things are falling towards the LMC. And so if we ever come a day where we have detections towards very distant HVCs, then yes, the reflex motion signal should emerge in a very similar way across the sky.
Nicola?
This model, can you say model experimental leading arm?
Oh, the leading arm.
Yeah.
Ah, yes. So we mostly avoided much conversation about the leading arm because we don't include the SMC and we don't include like cold gas and the ISM, and so I think trying to model that was a bit hopeless. But I definitely do think in future iterations of the model, which do include those additional components, we'll actually be able to say something a bit more meaningful about the leading arm and potentially its ionized gas component.
Yeah.
That was great. So do LMC or SMC pulsars have excess dispersion measure compared to pulsars in, say, the most distant off-plane clockwork clusters?
That would be my question to you, right?
I mean, it would require some modeling, but the data exists.
Yeah. Yeah, good. Love to talk more about that.
Yeah.
This kind of phenomenon has been studied in great detail with Chandra and XMM in nearby groups and galaxy clusters. And one of the factors that we've sort of uncovered is that many times that we look at the merging, infalling galaxies and clusters, a lot of times the data supports the case that this has to be the second or third infall. Okay. How do you know do we know that the LMC, this is actually the first pericenter passage? That maybe it's actually gone around a couple times already, and so it's already essentially shock heated the CGM, perhaps.
Yeah, so many aspects to that question, and so I think this goes back to where I started at the beginning of the talk, talking about our improvements in proper motion measurements of the LMC, and it seems like there's a very narrow range of possible orbits that actually get you close to its observed positions and velocities along the sky. And those orbits tend to be either first infall orbits or orbits which had a prior passage long ago in the past. And so I think that, in addition to how gas-rich the LMC and the SMC are, I think are strongly suggestive that they are recent neighbors to the Milky Way.
Okay.
Yeah, and also a lot of the shocks seen in groups or in clusters, they tend to be strongest on first infall.
Absolutely.
Yeah.
Absolutely. Yep.
All right, let's thank Chris again.